In chapter 1, as I said, it's about first order ordinary differential equations. In this chapter, we're going to talk about these topics. First, in section 1, we have the basic definitions and terminologies. In second section, it's about types of first order ordinary differential equations and methods of solution. In this section, we talk about 5 methods for solving first order ordinary differential equations. These are the methods. And then in the last section, we have applications of first order ordinary differential equations. We have Newton laws of cooling, natural growth and decay, electronic circuit model, and also vertical motion. This is also about Newton's second law of motion. First, we have some basic definitions and terminologies. What's a differential equation? We say a differential equation is an equation which includes derivatives. Sorry? Yes, of course. We say a differential equation is a function include derivatives and also functions. Here, in an ordinary differential equation, we say it contains one or more dependent variables, and also with respect to one independent variable, here we have the derivatives. We have derivatives with one of the independent variables. As you see here, this is an ordinary differential equation. Its order is 1. Order is the highest derivative in the equation. Order is the highest derivative in the equation. Here we have dy by dx. This is derivative equals 2x plus 3. This is an ordinary differential equation. And here, y is the dependent variable. Y is the dependent variable, and x is the independent variable. Here, when we say d, let's say a by db, that's generally, I talk about this. A is the dependent variable, and b is the independent variable. Okay? And here you have dy by dx. That means y is the dependent variable. Y is the dependent variable and x is independent variable. It equals 2x plus 3. It's a first order ordinary differential equation. And here we have d squared of y by dx squared equals the second one. We have d squared of y by dx squared plus 3 dy by dx plus ay equals 0. Here a is a constant. It's a constant. The dependent variable here is y, and the independent variable is x. And here, the order of this differential equation, as I said, it's the highest order. The highest, order is the highest derivative. The highest derivative here is 2. As you see here, it's the second derivative. It's d squared of y by dx squared. So the order of this differential equation is 2. The independent variable is x and the dependent variable is y. You have another example. It's d cubed of y by dx cubed plus dy by dx to the power 4 plus 6y equals 3. Here, as you have dy by d something, means y is a dependent variable. And x, what's in the denominator, was dx in the denominator, means x is independent variable. And the order of this differential equation is 3 or 4. It's 3, yeah. This 4 is power. It's not derivative. Here we have first derivative, which is raised to the power 4. But the order is 3. As you see here, we have third derivative. That means the highest derivative here is 3. And also we have partial differential equations. Up to now we talked about ordinary differential equations, and now we have partial differential equations. In partial differential equations, we have one or more dependent variables. We also have two or more independent variables in partial differential equations. Here we have some examples about partial differential equations. Here we have partial square root of u by partial x squared plus partial square root of u by partial y squared equals 0. Here, u is dependent variable. X and y, as you see, we have x and y in the denominators. That means x and y are both independent variables. We have only one dependent variable and two independent variables in this equation. In the second one, we have partial to the power 4 of u by partial x to the power 4 plus partial to the power 4 of u by partial t to the power 4. Here, u is the dependent variable, and x and t are independent variables. For the first one, for this one, what's the order of this partial differential equation? Order is the highest derivative. In both terms, you have second, you have second derivative, second partial derivative. That means the order of this partial differential equation is 2. And for the second one, for this one, the order is 4. And for the last one, the dependent variable is u, and the independent variables are x and t. Okay, and here the order of this partial differential equation is 2. Now you have solving these equations. We are going to write down the dependent variable and independent variable for these partial differential equations. For the first one, we have partial w by partial x plus partial w by partial t. We have this, which is the same as to say w sub x plus w sub t equals 0. And these are the same. Here, the dependent variable here is w. The independent variables are x and t. No. Yeah, yes, here we have t, not y. Yeah, but you should write down the given. Yeah. Yes, this one you mean. It's the same as this one, yes. But here, you should write down the given variable, not one, okay? For the second one, we have partial square root of u by partial x squared. It means we can write down this as u sub xx, okay? And here we have partial square root of u by partial x partial y. We can say it equals u sub xy. Look here, cx and y. We write down the same as the same order. Then we have partial u by partial y, which is u sub y equals e to the power xy. As you see, it's written down here. So the dependent variable here is u. The dependent variable is u, and the independent variables are x and y. Okay. Now you have order of a differential equation. Order of differential equations. The first one, the order of this differential equation is 1 because the highest derivative is 1. For the second one, the order is 2 because the highest derivative here is 2. But for the last one, as you see, it's 3. Here it's the first derivative. It's first derivative, which is raised to the power 4. So this power, this is power, it's not derivative. That means here, this is the highest derivative, and the highest derivative here is 3. Okay. Now we have degree of differential equation. We say degree is the exponent of the highest derivative. It is the exponent of the highest derivative. If you return to the previous one, for this one, what's the degree here? The highest derivative is 3. So what's its exponent? It's 1. It's not 4. So the degree, we don't count the highest degree randomly. We should know what's the highest derivative, and then we just take the exponent of the highest derivative. Here, the highest derivative is 3, and its degree is 1. So the degree of this differential equation is 1. I'll turn to here we have some examples. For the first one, we have d squared of y by dx squared plus 3 dy by dx plus ay equals 0. Here, the order is 2. We should know the order before finding the degree. The order is 2, and the degree is 1, is the exponent. As we have no exponent here, means its exponent is 1. So the degree is 1. The second one, we have d cubed of y by dx cubed plus dy by dx to the power 4 plus 6y equals 3. In this differential equation, the order is 3. As here, we have the highest derivative is 3. What's the exponent of this derivative? It's 1. So its degree is 1. This is the degree of that differential equation. And the last one, we have d squared of y by dx squared to the power 3. And dy by dx to the power 5 plus 3 equals 0. Here, the highest order, the highest derivative, which the order is 2. The order is 2. And the degree is 3. So the degree of this differential equation is 3. That's it. It's how to find order and degree of differential equations. And here we have some more examples. Here, in these two examples, we should find order and degree of these differential equations. The first one is an ordinary differential equation, and the second one is a partial differential equation. You have dy by dx squared plus y equals sine x. Here, the order is the highest derivative. We have only one term of the derivations, which is dy by dx, and its order is 1. Order is the highest derivative, and degree is the power of that highest derivative, which is 2. The degree is 2. Then we have partial square root of u by partial t squared plus u squared equals cos t, cosine t. Here, the order is 2. How about the degree? It's 1. Since it has no exponent, means its exponent is 1. Okay? Now you have this also. For this partial differential equation, the order is 2. The highest derivative is 2. The highest partial derivative is 2. And the degree of the highest partial derivative is 1. We just count the degree of this derivative, which is 1. For the last one, we have partial cubed of z by partial y cubed to the power 4 plus partial z by partial y squared plus z equals 0. What's the order of this partial differential equation? Order is the highest, which is the highest derivative, which is 3. And degree is 4. Degree is 4, which is the degree of the highest derivative. Now we have linear and non-linear differential equations. Okay. We now have linear differential equations. We should recognize whose differential equation is a linear first order differential equation or a linear differential equation, and what's not a linear differential equation. We have these two conditions for the linearity of a differential equation. We say the dependent variables and their derivatives must have degree 1. So the degree of the derivatives and the independent variables must be degree 1, and their degree must be 1. And also the coefficients of the derivatives, depends only on the independent variables. That means we must have either constants or independent variables as the coefficient of the derivatives. If any equation satisfies these two, it means that differential equation is a linear differential equation. Here we have some examples. The first one, we have d squared of y by dx squared plus 3 dy by dx plus 9y equals 0. Let's check if this equation satisfies this condition or not. The first condition is says that the dependent variables and their derivatives must degree 1. Look, this is derivative of the dependent variable. This is also, and this also dependent variable. Here in this equation, y is the dependent variable. The degree of y and all the derivatives is 1. That means it satisfies the first condition. For the second condition, we say the coefficients of derivatives must be constants or independent variables. Here, the coefficients of the derivatives, for this one, its coefficient is 1. And here, the coefficient is 3. That means that this differential equation is a linear differential equation. For the second one, as you see here, we have degree of this derivative, which is not 1. It's not 1. It's 4. That means it's nonlinear. It is nonlinear because we have a degree of a derivative which is not. Okay, it's nonlinear because this is the reason. Must satisfy both. Yeah. Just for linear, yeah. This one. This is not linear. Why? No, x is okay. X is okay to be squared. But here we have this coefficient of this derivative, which is not the independent variable. It's dependent variable. If we have dependent variable which is multiplied by derivatives, we say that differential equation is not linear. It's not linear. Why? We say since y is the coefficient of dy by dx. This is the reason. We say here, look at the second condition. The first condition is okay for this one, for this differential equation. It satisfies the first condition. But for the second condition, it says each coefficient of the derivatives must be independent variables or constants. Okay, and here this coefficient وقتها هقول كبردم نص بردمي هنا that okay. This coefficient is y. This is y, and y is not independent variable. It's a dependent variable. you should first recognize what is the dependent variable and what is the independent variable. Here, the dependent variable is y, and the independent variable is x. Here we have dependent variable which is multiplied by a derivative. That means this is not a linear function, a linear differential equation. It's non-linear. For this one, we say dy by dx equals sine y. If we have the dependent variable as the angles of trigonometric functions, and also if this in a root, and even if this the angle of length or logarithm, or if this the exponent of e, it means the degree of that dependent variable is not 1. Here, the degree of this y is not 1. The degree is not 1 because it's the angle of sine function. Here, we say this differential equation is nonlinear. Why? Because the degree of this dependent variable is not 1. It's angle of sine. And if we expand this, we say sine y equals y minus y cubed over 3 factorial plus y to the power 5 over 5 factorial minus y to the power 7 over 7 factorial. And so this is the expansion of sine function. That's why we say it is degree is not 1. No, for cosine is 1 minus. For example, if you have cosine y equals 1 minus y squared over 2 factorial plus y to the power 4 over 4 factorial minus y to the power 6 over 6 factorial. This is the yes. If we have the dependent variable, only the dependent variable, if you have x in the as the angle of sine and cosine, it's okay. But for y, which is the dependent variable here, we say it must not be the angle of trigonometric functions. Even it must not be the angle of length or logarithm. Okay, and also it must not be in a root. Yes. Yes, if you have y, if you have the dependent variable in the angle, we say that's nonlinear. Sine, yes, it's okay. If it is sine x, that's okay. But for y, we say the differential equation is nonlinear. And for this one, let's check. This is okay. Look, for the first condition, just a minute, we say the order, the degree of all derivatives. Look, the degree of this derivative is 1. For this derivative, its degree is 1. For this one is 1. And even for y, its degree is 1. It's okay. So it satisfies the first condition. How about the second condition? For the second condition, we say the coefficients of derivatives must be the independent variables. The independent variable here is x. That means if you have x as the coefficient, it's okay. For this one, it's okay. This one is okay. This one is okay. And here, it's exponential of x. It's okay. But if you have exponential of y, we say that's not linear. We say that's not linear. And here, we say this differential equation is a linear. Why? Because it satisfies both conditions. Look, this is y. Its degree is 1. The degree is 1. It's not an angle. Okay. So we say this is a linear. This is a linear differential equation. We say other than linear differential equation is a nonlinear differential equation. If it's non-linear, means that is a nonlinear differential equation. And now we have initial and boundary value problems. We have initial and boundary value problems. Here first we talk about initial condition and boundary condition. This is an initial condition because both are 0 here. Both are the same number. If both are the same number, means it is initial condition. If, for example, y of something and then y prime of something. If both are the same, I mean this was in the bracket. If both are the same, we say that's initial. Okay. Alain اجد كاتي يعني y of شتى زائد ياخذ y prime of شتى اجد هاتوا امريكا همانا امريكا قال y prime مكاننا وكان كان شتى اجد هاتوا هدف يكشفوا او بيوتي initial. اوكي يعني صفر بلين اجد صفر بو بي او تريد initial condition بلان اجد هاتوا جواز بو او بي او تريد شيء boundary condition. I'm a boundary condition. Okay. And for initial value problem and boundary value problems, we can recognize them by the conditions. If it is initial condition, we say it's all together is an initial value problem. All together is an initial value problem. This is the initial condition. Okay, and for the boundary value problems, we can recognize it by checking the conditions, boundary conditions. Here, as you see, it's different. It's y of 0 and y of 1. They are different. That's why we say it's all together is called a boundary value problem. It's initial and boundary value problems. Okay. Did you get that? Okay. Now we have section 2. As I said, we have 5 methods for solving first order differential equation. First is separable equation. Second is homogeneous equation. Then exact equation, linear equation, and Bernoulli equation. The most important thing here is to recognize the equation. Recognize the equation is either one of these. Okay, maybe we have some equations that could be solved by more than one method. Okay, so first we have separable equation. In separable equation, here we are gonna put dx with x terms in one side of the equality and y terms with dy in the other side of the equality. If you could separate y and x and we put y with dy, x with dx, that means that differential equation is separable. Here, as you see, we have v of y dy and u of x dx. That means here we have a function of x and here we have a function of y with dy. If you could separate them, that means that differential equation is separable. Here we have these 6 examples. It's about just separating the variables. It's not about solving them. Okay, after separating them, we just take the integration of both sides and you'll get the result. We just take the integration for both sides, we get the result. For the first one, بس جاي كذا ونجي جديد x تقل dx ثابت همو x كان لقل dx ثابت وبتوان بنوسم وهمو y كان لقل dy كيك وبنوسم دواتر integral dx. والله ليه أنا شو example تنها جاي كذا x dx y dy. Okay. For the first one. we have dy over dx a. dy over dx equals secant squared of y over 1 plus x squared. First of all, we should multiply both sides by dx. If we have dy by dx, dy over dx, we must multiply both sides by dx first. We multiply both sides by dx. What we get? We get dy equals secant squared of y by 1 plus x squared dx. We get this. We just multiplied both sides by dx. In the left hand side, it's going to be cancelled out with the denominator, and in the right hand side, we just get dx. Now, in the left hand side, you have dy, and in the right hand side, you have dx. But we must have no y terms with dx. Okay? And also, we must have no x terms with dy. With dy, we have no x terms. It's okay. But in the right hand side, we have y term, which is secant squared of y. We must remove this one here. How? We divide both sides by secant squared of y. If we divide both sides by secant squared of y, we can remove that secant squared of y in the right hand side. That means we divide both sides by secant squared of y. Now, what we get if we divide both sides by secant squared of y, we get dy over secant squared of y. In the left hand side, we get dy over secant squared of y. And in the right hand side, we get 1 over 1 plus x squared dx. As you see, we could separate them. In the left hand side, we have dy and y terms. And in the right hand side, we have x terms and dx. That's all. It's just about separating. In this example, we are asked to just separate the variables, not for solving it. Here, we just take integration for both sides, you get the result. Okay? For B, in the other examples, in the next examples, we will solve the differential equation. Here, it's just about separating the variables. B is x dv by dx, x dv by dx equals 1 minus v squared 4v squared over 3v. This is the equation. To separate the variables here, what are the variables here? X and v, and we have dv and dx. So we must put all v terms with dv and all x terms with dx. First of all, we should multiply both sides by dx. Here, we multiply both sides by dx. What we get x dv in the left hand side, and in the right hand side we get 1 minus 4v squared over 3v dx. And now we must have only x terms with dx, and we must have only v terms with dv. We have this x here. How to remove this? We divide both sides by x. Okay, we divide both sides by x. To remove this x term with dv, we divide both sides by x. And here we have this fraction, which includes v. How to remove this? We can divide, or we can multiply it by its inversion. Okay, we can multiply it by 3v over 1 minus 4v squared, is it? Or we can divide by itself. Now, if we divide both sides by x, what we get? In the left-hand side, we just get dv. Okay? Equals. In the right-hand side, we get dx over x. And if we multiply both sides by 3v over 1 minus 4v squared. Here, this is removed here. And in the left, we get 3v over 1 minus 4v squared. That's all. Okay? By multiplying both sides by 3v over 1 minus 4v squared and dividing both sides by x, we get this equation. And as you see here, we have no x with d, and we have no v with dx. So it's the separated form. For part C, for C, dx over dt plus x squared equals x. Dx over dt plus x squared equals x, is it? Yeah. This is part C. For this one, what we do, we should first multiply both sides by dt, or we can move this one to there first and then multiply both sides by dt. Both are correct. Let's follow the one which we did before. Okay? We first multiply both sides by dt. What we get? We get dx in the left and in the plus x squared dt. And in the right, we get x dt. Okay? As I said, we must put all dt in one side of the equality. So we move this to here because it includes dt. We get dx equals x dt minus x squared dt. Let me write down it. We say we get dx in the left equals x dt, and moving x squared dt to the right becomes minus x squared dt. And now, what's the cone in the right? dt is common between those two terms. We take dt as the common. dt. So dx equals x minus x squared dt. And now we try to put x terms with dx and t terms with dt. In the left, we have only dx, so that's okay. But in the right, we have x terms and dt also. We must remove this bracket here. We divide both sides by x minus x squared. We divide both sides by x minus x squared to remove these x terms in the right. And we get dx over x minus x squared equals dt. As you see, we could separate them. We have only x terms with dx, and we have dt in the right hand side. That's all. For part D, dy by dx equals 3x squared times 1 plus y squared. Dy by dx equals 3x squared times 1 plus y squared. We have this equation. What we do first, we multiply both sides by dx. And we get dy in the left-hand side, and in the right-hand side, we have 3x squared times 1 plus y squared dx. And in the right hand side, we have dx, but we have 1 plus y squared also. We must remove it there. How? We divide both sides by 1 plus y squared. We divide both sides by that bracket, and we get dy over 1 plus y squared equals 3x squared dx. That's all. Okay? Is that easy?
Yeah. Just like this one.
Yes. Just simplifying them. So e, it's y to the power negative 1 dy plus y equals x sine x dx. Yes. Yes, it's similar. Plus y e cos x y e cos x sine x dx equals 0. That's it. Yeah. Here we should first move dx with its coefficients to the right hand side. Okay. We get y to the power negative 1 dy equals minus y e to the power cosine x sine x dx. We can say y to the power negative 1 means over y, is it? This is y to negative 1. That means we can return to the denominator. Now, in the left hand side, we have only y with you. But in the right hand side, we have y with dx. That means we must divide both sides by y to remove this y here. And we get dy over y squared. Here we have dy over y. If we divide by y again, we get y times y in the denominator, it's y squared, equals minus e to the power cosine x sine x dx. This is the separated form. And for the last one, we have x plus xy squared dx. X plus xy squared dx. Plus e to the power x squared y dy. Now we have dx and dy in one side of the equality. We have no dy by dx. That's why we don't multiply both sides by dx. ليه dy لسه dx معنيه لبر أوية كم step هدول أزار dx تاني. Okay. We have dx and dy in one side of the equality. So we move one of them to the other side. Let's move this one to the other side. Moving this to the other side. So we get e to the power x squared y dy equals x plus xy squared dx. It's minus. Sorry. هل كان فرق هنا؟ Yeah, it's the same. No problem. Here, what should we remove in the left hand side? A to the power x squared, because it includes x, and it must not be with dy. And in the right hand side, we have y squared. So here we take x as the common. We take x as the common between these two terms in the right hand side. We get, I'm just gonna write down here. If we take x as the common between these two terms, what we get? we get e to the power x squared y dy equals minus x, what's left? 1 plus y squared dx. And now we can separate the variables. How? We can remove this one here. We divide both sides by e to the power x squared, and we also divide both sides by 1 plus y squared. So we divide both sides by e to the power x squared and 1 plus y squared. So in the left hand side, we just get y dividing by 1 plus y squared. We get y over 1 plus y squared dy equals, in the right hand side, we have minus x over e to the power x squared dx. This is the separated form. Okay, that's how to separate the variables. I mean, x with dx and y with dy. After this step, you just need to take integration from both sides. That's the result. You'll get the result, or you will get the solution for the differential equation. Here you have an example. We have given an initial value problem, and we should solve it. The condition, the initial condition, is given for only finding the constant that you get after taking the integration. Here, we use this at the last step. In the last step, we use that for finding the value of the constant that you get during the integration, taking the integration. First, we should separate the functions, the variables. We have dy over dx equals y cos x dividing by 1 plus 2y squared. First, what we do, we multiply both sides by dx, multiplying both sides by dx, and we get dy equals y cos x dividing by 1 plus 2y squared dx. And here with dx we have y over 1 plus y squared, 2y squared. We must remove this here. How? We multiply both sides by 1 plus y, 2y squared over y. We multiply both sides by 1 plus 2y squared over y. So what we get? We get dy 1 plus 2y squared over y dy. In the left hand side, we get this. And in the right hand side, we get cosine x dx. That's all. Okay, this is the separating of the functions or dx and dy. This is in the first step. In the second step, what we do, we are going to take the integration for both sides. We are going to take the integration for both sides. So we say the integration of 1 plus 2y squared over y dy equals the integration of cosine x dx. In the left hand side, we are going to take the integration with respect to y, as we have dy. And for the right hand side, we take the integration with respect to x, as you have dx. For the left hand side, first we should simplify it, then we take the integration. We say we get this denominator is for both terms in the numerator. It's for 1 and it's also for 2y squared. We can give the denominator for each, or we separate the terms. We get the integration of 1 over y plus 2y squared over y. And we can say it is 2y, is it? I'm just going to write down 2y. Okay? Here, this denominator is for both 1 and 2y squared. It's 1 over y plus 2y squared over y. Here, we get 2y squared over y. This with this one is cancelled out, So we get only 2y here. This is dy equals cosine x dx. Now we can take the integration. The integration 1 over y is ln y. It's ln y. It's ln y. Yeah. We say it equals ln y. How about the integration of 2y? It's 2y squared over 2, which is only y squared. Equals cosine x. Its integration is sine x, because the derivative of sine is cosine. So integration of cosine is sine x plus c. This is the result. This is the solution. That's the general solution. But here in this example, we have given a condition. We should apply this condition to find the value of c. We use this condition for only finding the value of c. That's all. Okay? To apply the condition, here we have given y of 0 is equal to 1. That means we replace x by 0 and y by 1 in this equation. Okay? In the result equation, we just replace x by 0 and y by 1. It's given in the example. If it's not given, so we just leave the solution like this. This is the final answer. If the condition is not given, if it is not an initial value problem, we have given only the differential equation, we just leave this one as the result, as the final answer. And here we replace x by 0 and y by 1 here. We get ln 1, let's do it. Ln 1 plus 1 squared equals sine 0 plus c. Here we apply the condition for only finding the values of constants. Ln 1 is 0 and sine 0 is still 0. That means 1 squared is 1 equals c. So c is 1. We return c to this equation and it will be the final answer. Look, ln y plus y squared equals sine x plus c. C here is 1. As you see, this is the final answer. So you get ln y plus y squared equals sine x plus the value of c, which is 1. This is the final answer. For what? For the integrations? There is no a complicated ones here. Okay. All are those which you took before. Yes. Sorry. We are just going to talk about this example and it should be enough for today. No. No. First, you should solve it and then find the values. How much? Yes. Okay. So it's only one example about the same topic. That's why I want to talk about. It's okay.